This Python code prepares an environment for a data analysis and machine learning project by importing various libraries and modules. The imports are summarized as follows: NumPy for numerical computing, Pandas for data manipulation and analysis, Sklearn for preprocessing and model selection, Matplotlib for plotting, DataTime for working with dates and times, and Seaborn and Plotly for visualization. It also configures the display and warning systems for a Jupyter Notebook environment. The following code in Python uses the setIndex method to change the date column to the new index for a data frame called dateIn from the Pandas library. It then uses the shed method to display the first 5 rows of the modified data frame. The number of rows shown can be adjusted by providing a numeric argument to the shed method. The data info code in Python most likely uses the shinfo method on a Pandas data frame called dateIt. It gives a brief summary of the data frame, including the number of entries, non-null entries per column, column data types, and the data frame's memory usage. This function is valuable for obtaining a fast overview of the data frame's structure and contents, especially when working on data cleaning and exploration in a data analysis project. The provided Python code rearranges the columns of a data frame named data by using a predefined list called bulkorder containing the columns date and @close. This is achieved by using the shreindex method, which updates the order of the columns based on the list. The updated data frame is then saved back to the original variable. This Python code snippet uses the diff method to perform a difference transformation on the @close column of the data frame. This transforms the data into a stationary time series by calculating the change in value between each row and its predecessor. The resulting values are stored in a new column called difference transformation demand. The head method is then used to display the first few rows of the data frame, including the newly created column. However, the results are not stored or printed in the code, so the snippet must be run iteratively or using the print function for the output to be shown. This Python code uses a Pandas data frame named data to create a new column called different demand filled using imp, where function. It fills the new column with values from the @close column if the corresponding values in the difference transformation demand column are null. Otherwise, it simply copies the values into the new column. The code also displays the updated data frame using the head method. The Python code manipulates data in a Pandas data frame named data to convert it for demand forecasting. It performs a cumulative sum on one column and stores the result in a new column, which reverses a previous differencing operation. The code then uses numpy's search function to check if the transformed data matches the original data. This ensures the transformation was successful. This Python code snippet imports various libraries for data analysis and visualization. 1. A Pandas is shipped to a library for manipulating and analyzing structured data, particularly tabular data with different column types such as CT and SIL files. 2. NumPy is used for numerical computing with support for arrays, matrices, and mathematical functions. 3. Statsmodules. API is includes classes and functions for statistical modeling, testing, and data exploration. 4. Statsmodules. Formula. APIC is a submodule that allows fitting of statistical models using your style formulas. 5. Sklearn. Metrics is metrics part of the scikit-learn library. This includes score and performance metrics, and distance computations. 6. Seaborn is a data visualization library based on Matplotlib, offering a user-friendly interface for creating attractive and informative graphs. 7. Matplotlib. Pyplot is a module for plotting 2 data visualizations from the Matplotlib library. The final line, Matplotlib inline, is a magic function for the Python interpreter to display figures within the notebook instead of opening them in a new window. This allows for seamless plotting and viewing of graphs in the notebook. This code configures the Matplotlib library for plotting graphs in a Jupyter Notebook or similar environment. It sets the figure size and enables a grid for all plots by default. The command in Matplotlib inline ensures that plots are displayed directly in the notebook. The following Python code snippet uses Matplotlib, imported as Spult, to plot time series data. It creates a 20 by 10 inch figure with axes for plotting. The code then plots a gray line for the difference transformation demand column in the data frame. Starting from the second data point, It also calculates and visualizes the simple moving average and rolling standard deviation for the same time series over a window of 20 points. A legend is added to label the lines for clarity, and the final result is a plot that showcases the original data, its short-term trend and variability over time. This Python code uses a plotting library, likely Matplotlib, to create a chart. It first sets up a figure and axis with a specified size. Then, it plots the values from a data frame called data feature isolated using a gray color, starting from the second element. Additionally, it calculates and plots the rolling mean and standard deviation of these values with a window size of 20, showing the average and variability of the dataset. The rolling mean is represented with an orange line and labeled rolling mean, while the rolling standard deviation is shown in yellow and labeled rolling STD. The plot also includes a legend with a font size of 12 for easy identification of the plotted lines. The Python code includes a function called kipstist for performing the kipst test on a time series to determine if it is stationary around a trend or mean level. The function uses the statsmodels module to run the test and display the results, including the test statistic, value, number of lags, and critical values for different confidence levels. A conclusion is provided based on the p-value with a value below 0.5 indicating non-stationarity and a value equal to or greater than 0.5 suggesting stationarities. The provided code example assumes that the input is a univariate time series from a specific column in a data frame. This Python function, to build temporal features, takes a pandas data frame as input and returns a modified version of the original with additional time-related features. It first converts the date column to a pandas datetime object and then creates new columns for the year, month, week, number, day of the month, and day of the week. It also calculates the week of the month for each date and identifies weekend dates with a binary indicator. The result is a data frame with these new temporal features. This code snippet utilizes the pandas library or a similar data processing tool to perform two key tasks. Firstly, it applies the function to build temporal features to the variable data feature isolated, likely to generate temporal features from the input data. These features could include year, month, day, day of the week, etc. Secondly, the resulting data frame found, containing the newly created temporal features, is passed into the shed method, which displays the first few rows of the data frame for easy inspection and verification. This Python code generates a distribution plot of the column different demand filled in the data frame found. It uses the Seaborn library and sets the figure size to 10 inches by 8 inches. The plot represents the frequency distribution of the selected column and has a title of distribution plot adi closed if couple. The appearance of the plot is enhanced by adjusting the font scale and sizes for the axis tick labels. This improves readability. This Python code prints rows from a specific pandas data frame to phones. Based on a filter created using the date column, the filter selects rows with a date between January 1st, 2010 and December 31st, 2021. The filter is a Boolean mask that is applied to the data frame to retrieve the matching rows. Using the slow function, the resulting rows are then printed. This Python code demonstrates how to scale a set of values called y into a desired range, which in this case is between 0 and 1. It uses the widely used min and max scalar from the scikit-learn library for this purpose. The first step is to import the scalar from scikit-learn preprocessing. Then an instance of the scalar is created with the specified feature range. The values in y are converted into a numpy array if they aren't already, and reshaped into a 2D array with one feature per column. The min-max scalar then scales the data using the fit transform method, which calculates the minimum and maximum values of the input and applies the scaling accordingly. The result is a scaled version of y within the desired range, which is advantageous for machine learning algorithms that are sensitive to data scale. This snippet of Python code prepares a dataset called y for machine learning by dividing it into two parts, one for training and one for testing. The dataset y should be a two-dimensional array with rows as samples and columns as features or data points. The training size is determined as 65 of the total number of samples, and the test size is calculated by subtracting the training size from the total number of samples. The dataset is then split into two parts: trained data representing the first 65 of samples, and test data representing the remaining samples. In machine learning, trained data is used for training the model and test data is used to assess the model's performance. The code assumes that the dataset Y is indexed by rows and uses appropriate slicing syntax to maintain the original number of columns. The function treated dataset in Python takes a two-dimensional array-like dataset and a schema step parameter to structure the data for time series forecasting. It creates two arrays, a data X and data Y, where each element in data X contains a subsequence of schema-stepped consecutive values and each element in data Y contains the next value after the subsequence. The function converts the arrays into NumPy arrays and returns them, providing a suitable format for training machine learning models on sequence prediction tasks. This allows models to predict the next value in a sequence using the previous schema-stepped values. This Python code sets a variable, schema-step, to a value of 100 and uses it to call the created dataset function twice, providing it with trained data and test data. This function likely modifies the data to create training and testing datasets suitable for a machine learning model. The results are then stored in four variables: text-trained and g-trained for the training dataset, and test and t-test for the testing dataset. The given code reshapes two variables, text-trained and t-test, by adding a dimension of size 1. This is a common practice in machine learning to meet the input requirements of certain models, such as convolutional neural networks. The new shape of the variables will have 3 dimensions, with the first dimension representing the number of samples, the second dimension being the original features or time steps, and the third dimension being the added channels dimension. This transformation makes the datasets suitable for models that require a singleton dimension in the input data. This code is used for importing specific functions and classes from various libraries commonly used for deep learning and preprocessing in Python. It sets up the creation of a neural network using the TensorFlow framework in Keras as its high-level API. The imported items are 1. Sequential from TensorFlow, Keras, models, which creates a linear stack of layers in Keras for modeling. 2. Dense, dropout, batch normalization, and LSTM from TensorFlow, Keras, layers, with each layer having a specific purpose in neural networks. 3. Min-max scalar from Sklearn, preprocessing, which scales features within a given range to aid neural network convergence. 4. Random normal and constant from TensorFlow, Keras, initializers, which define the initial weights for Keras layers. These imports provide the necessary components to build, train, and evaluate a neural network model that may use a combination of dense, dropout, batch normalization, and LSTM layers with properly initialized weights and scaled input features. This code snippet creates a neural network using Keras for sequential data. The network is made up of LSTM layers, which are suitable for learning from sequences. It also includes dropout layers for regularization. The network is compiled with the mean-squared error loss function and the atom optimizer. This setup is ideal for a regression problem involving time series prediction. The Python code snippet utilizes the Shirley stopping callback from the TensorFlow Keras cappies. This callback is employed during machine learning model training to end the process if a specific criterion, like lack of improvement on a validation set for a set number of epochs, is met. This aids in avoiding overfitting and saving time by stopping training when no further progress is occurring. The given code utilizes a Python snippet to create an early stopping callback, named monitor, which halts the training process of a machine learning model if a specific condition is met. This condition, in this case, is when the validation loss stops improving beyond a certain threshold. The callback is configured to monitor the validation loss value valcloss and requires a minimum improvement of 0.1 min delta over 30 consecutive epochs patience. If the validation loss does not meet this requirement, training is terminated with a log message output verbose is set to 1. The callbacks mode is set to auto, allowing it to determine if the monitored metric should be minimized or maximized. The restore best weights setting ensures that the model's weights are reverted to the best opposed values once training is stopped. Finally, the model is trained using a model, fit and is surely stopping callback. With a maximum of 1000 epochs and performance metrics reported verbose is enabled. Overall, this code implements an early stopping mechanism in training the model, potentially preventing overfitting and saving time. The code saves a machine learning model in an HFI file called listen 2022.5. This is commonly done after training the model to allow for loading and use without retraining. The 5 extension suggests that the model is an LSTM network, a type of recurrent neural network used for predicting sequences. The D5 format is suitable for storing large numerical datasets in deep learning models. This Python code creates a graph to track the performance of a machine learning model during training. The graph displays the training loss and validation loss over time, with the x-axis representing the number of epochs and the y-axis representing the loss value. The graph is titled Model Loss with labeled axes and a legend to differentiate between training and validation loss. The graph is displayed using show. This code snippet uses matplotlib to visualize the training process of a machine learning model. A graph is created with 2 lines representing the training loss and validation loss over a number of epochs. The training loss comes from the loss attribute of the history object, while the validation loss is from valclass. The graph is labeled with a title and axis labels, and a legend is included to differentiate between the training and validation data. The plot is displayed using show, providing insight into the model's learning and potential overfitting or underfitting. This code uses the matplotlib library to produce a graph showing the training and validation loss of a machine learning model throughout multiple epochs. The plot includes titles and labels, as well as a legend to distinguish between training and validation data. The graph is then shown to the user. This code snippet in Python utilizes the matplotlib library to generate a graph that displays the training and validation losses of a machine learning model throughout the training process. The first plot command illustrates the loss values from the training history, while the second plot command, although partially commented out, shows the model's performance on a separate validation dataset. The title command names the graph as model loss, and tilable and checklable label the y-axis and x-axis as loss and epoch, respectively. A legend adds a legend to the graph with labels train and test, and it appears in the upper left corner. Finally, show displays the graph. This graph can help in evaluating the model's learning progress and identifying if it is overfitting or underfitting the training data as the epochs advance. This code utilizes the matplotlib library in Python to create a visual representation of the training loss of a machine learning model as it progresses through each epoch. An epoch refers to the model being trained on the entire training dataset. The line plot history, historic loss plots the loss metrics from each epoch, while klebelpos and tilabelos add labels to the x and y axes, respectively. The line show displays the plot for the user to see the change in loss over epochs. This code is helpful in understanding the model's learning behavior and convergence. This code displays a line graph of the loss of a machine learning model over each epoch during training. It uses the plot function from the matplotlib library and includes both training and validation loss values. The title and axes of the graph are labeled and a legend is created to distinguish between the 2 types of loss. This visualization allows the user to track the model's performance and spot any issues with overfitting or underfitting. This Python code plots the training and validation loss of a machine learning model over multiple epochs. Using the matplotlib library, a line chart is created with the number of epochs on the x-axis and the loss value on the y-axis. The code consists of several components, including lines to plot the training and validation loss values, set the title and axis labels, and add a legend. By interpreting the resulting chart, one can gain insights into the model's training progress and generalization abilities. This Python code uses a machine learning model to predict outcomes for 2 datasets. The first line predicts for the training dataset, xtrain, storing the results in train predict. The second line predicts for the testing dataset, xtest, storing the results in test predict. These predictions can be used to evaluate the model's ability to learn from the training data and generalize to unseen data by comparing them to known outcomes for both datasets. This code uses a scaler to convert predicted values from a scaled range back to their original scale for both the training and test data. The initial data may have been scaled for machine learning purposes, and the inverse transform method helps to reverse this process and make the predictions more interpretable and easier to evaluate. This Python code snippet uses the gmath library to import mathematical functions and the mean-squared-error function from the sklearn metrics module, which is part of the scikit-learn library. The mean-squared-error function takes trained and train predict as arguments. which are typically arrays or lists containing the true target values and predicted values by a regression model for the training dataset. It then calculates the mean squared error maze and takes the square root using the search function from the GMath library, resulting in the root mean squared errors. This is a commonly used metric to measure the performance of a regression model, with a lower rums indicating a better fit between the model and the data. This Python code snippet uses a function from the scikit-learn library to calculate the mean absolute error between a set of true values and predicted values from a regression model. This metric helps evaluate the accuracy of the model by determining the average difference between the two sets. A lower may indicates better model performance. The provided Python code calculates the mean absolute error made between two sets of data, the actual values you train and the predicted values train predict. This is achieved by utilizing the mean absolute error function from the metrics module in the scikit-learn's library. May is a commonly used metric for assessing the precision of a regression model, indicating the average size of the errors in a set of forecasts. Disregarding their direction, it is calculated as the average of the absolute differences between the predictions and actual observations, with each difference being equally weighted. The code above uses Python and the scikit-learn library to import and call the means absolute error function, which calculates the average difference between predicted and true values. It takes into arrays of values test for true values and test predict for predicted values. The resulting mean absolute error may gives an idea of how accurate the predictions are, and a lower may indicates better model performance. This function is commonly used in machine learning tasks. This Python code computes the rums between predicted and actual values for a training dataset. It imports the necessary modules and functions, calculates the mean squared error, and then takes the square root to obtain the rums. A lower rums indicates better performance of the predictive model. This Python code calculates the root mean square error rums between two sets of data test and test predict. First, it computes the mean squared error maze between the actual and predicted values. Then, the square root of the maze is taken using the search function from the GMath library. This resulting rums value has the same units as the original data and indicates the accuracy of the predictions, with a lower value indicating better performance. Rums is commonly used for measuring forecast errors and in regression analysis. The Python code visualizes predicted stock prices for Apple using a model. It creates a plot with 3 lines: the actual stock prices, training predictions, and testing predictions. The code determines the number of time steps to look back in the data and fills in values for the training and testing predictions. The plot includes a legend and labels for the axes. It aims to evaluate and compare the predictive model's performance on historical Apple stock prices. Python code is provided to visualize the results of a forecasting model, specifically for predicting stock prices. This is done by plotting the original data and predictions on a graph. The code, which is explained step by step, defines a variable for the number of time points considered in the model's prediction, creates a plot with specific dimensions, prepares arrays for the predictions, and plots the data and predictions on the graph. Additionally, the x and y axes are labeled accordingly and a legend is included. The resulting plot can be used to assess the accuracy of the model's predictions for both the training and test datasets. The performance of the machine learning model is being assessed using the mean squared error maze on 2 datasets: the training set iTrain and the test set iTest. The verbose shown option logs the progress during evaluation. The results are stored in trainings and tests variables to understand the model's performance on both trained and unseen data, helping make informed decisions about its generalization ability. The Python snippet creates a graph using matplotlib to visualize the mean squared error of a machine learning model during training. Each line in the code adds a specific element to the graph, including a title, training and validation loss values, a legend, and the display of the final plot. This graph is helpful in assessing the model's performance and ability to generalize to new data over epochs. This code uses Python to manipulate the test data variable by slicing it from the 944th element to the end of the dataset. The slice is then reshaped into a new array with 1 row and an undetermined number of columns. 1 is used to calculate automatically. The code retrieves the shape of this new array, which will show 1 row and however many columns resulted from the reshape. The following Python code takes an input, xinput, and converts it to a list called tempinput. It then retrieves the first element from this list, assumably a more complex data type, and transforms it into a standard Python list. This converted list is then reassigned to tempinput. This Python code snippet is likely used for time series forecasting, making predictions with a pre-trained model. It creates an empty list, output, to store the predicted values and loops through 30 predictions. A sliding window approach with a window size of 100 is used to update the input data. If the input data has more than 100 items, the oldest data point is removed. The code properly formats the input for the model and uses the model predict method to make a prediction for the next time step. The predicted value is then printed and added to the input data list. This process continues until 30 predictions are made and the results are printed out. The code does not show how the input data is initially set up or the specific details of the model used. This Python snippet uses the NumPy library to create two sequences of numbers. The first sequence, called dayNew, contains integers from 1 to 100. The second sequence, daypred, contains integers from 101 to 130. Note that the provided code may result in a syntax error due to missing punctuation. However, it is assumed that the intention is to use NumPy's range function to create two separate arrays. The code uses the matplotlib library to plot two line graphs on the same chart. The x-axis values are from dayNew and daypred, and the y-axis values are from wide and output. Both the axis values are transformed back to their original scale using a scalar object before being plotted. This allows for accurate visualization of actual and predicted data points over time. The code transforms the variable y into a list and saves it as f3. Another list, output, is then added to f3 using the extend function. Finally, duplt is used to plot the elements in f3 starting from the 2001st element to the end of the list. However, the resulting plot is not shown or saved in this code snippet, and will likely be displayed or saved in a separate piece of code. This code uses the matplotlib library to create a graph showing both the actual and predicted stock prices of Apple over time. The graph has three different datasets plotted, including the real Apple stock prices, the predicted prices for the training data, and the predicted prices for the test data. The graph is titled Apple Stock Price Prediction and has labeled axes, a legend, and a command to display the graph for the user. Please note that there is a typo in the code spelling Apple as couple. The Python code snippet shown uses the matplotlib library to plot data related to stock price predictions. It first converts the normalized or standardized stock prices in the y dataset back to their original scale and plots them in green as the real stock price for Apple, likely a misspelling of Apple. Then, it displays the training set predictions in red and the test set predictions in blue, allowing for a comparison of the model's performance on both datasets. The graph's title, x-axis label, and y-axis label were appropriately set, and a legend is included to differentiate between the different lines representing real and predicted stock prices. The plot can be viewed using show to assess the model's accuracy. This snippet of code utilizes various imported modules and classes commonly used for creating LSTM models in Python, specifically for sequence prediction tasks. These modules and classes include random from the built-in Python library for random number generation, grade and chumsum from the numerical computation library NumPy, and a set of classes from chkuraj, a high-level neural networks API. These include the sequential model, LSTM layer, a dense layer, a time-distributed layer, and bidirectional wrapper. The code is likely a part of a larger script used for defining and training LSTM models for tasks such as time series prediction, text generation, or sequence-to-sequence learning. The network may be bidirectional, providing additional context by considering sequences in both forward and backward directions. This code snippet utilizes Keras, a high-level neural network API, to define a neural network architecture for a machine learning model. The functionality includes creating a sequential model with a bidirectional LSTM layer, setting the activation function to ReLU, and adding a dense output layer for predicting a single continuous value. The model is compiled with mean squared error as the loss function and Atom as the optimizer. This can be used for tasks such as time series prediction, where the goal is to predict future values based on past observations. This code uses an early stopping callback in Python, a tool for preventing overfitting during neural network training. The callback stops training if the validation loss does not improve by at least 0.1 for 30 consecutive epochs. The model's weights are then restored to the best epoch. The code then trains a model on the training data and evaluates its performance on a validation dataset. The maximum number of epochs is set to 1000, but training can stop earlier if the early stopping conditions are met. The progress of the training will be printed to the console. The training history is stored in a variable for further analysis. This code saves a trained Python machine learning model as Model 5 using a library like Keras. The use of the 5 extension indicates that the model is being stored in GEF5 format, a popular format for saving large numerical data like neural network weights. This makes it possible to load and reuse the model without needing to train it again. The given Python code snippet appears to be a part of a script pertaining to machine learning. It is specifically used to save the weights of a model, referred to as methyls weights. 5. This allows for the ease of recoding the weights into the model for future use, such as continuing training or making predictions without retraining from the beginning. The use of an GIF5 file format, indicated by the 5 extension, is common for storing large numerical datasets. As for the name methyls weights, it is likely chosen by the user and may not necessarily represent the final or main set of weights. However, without further context, it cannot be determined for certain. This Python code snippet utilizes Matplotlib's pyplot library to display the training and validation loss of a machine learning model as it progresses. The steps followed are 1. Setting the plot's title as loss mean squared error. 2. Plotting the validation losses test. 3. Plotting the training losses train. 4. Adding a legend to differentiate between the two data series. 5. Showing the resulting plot. This visualization aids in understanding the model's learning performance, overfitting or underfitting by tracking the decrease in loss for both datasets. This code produces a graph depicting the loss or mean squared error of a model during its training and validation phases over each epoch or iteration. The title of the graph is loss mean squared error and it includes 2 lines, one for validation loss valclos and one for training loss. These lines are stored in a variable named Historione, likely from a machine learning model trained using a library like Keras. The label argument adds a legend to each line for better differentiation. Displayed through the chpplot legend call, the graph is shown using chpplot show, assuming the use of Matplotlib for visualizations in Python. This Python code creates a plot to show the training loss, as measured by mean squared error of a model over time. The graph's title is set as loss mean squared error, and the loss values are obtained from a training history object. The legend labels the data series as train and the user is able to view the graph. This Python code is designed for data visualization, specifically for plotting a graph that shows the loss mean squared error of a model during validation. The script sets the plot title, plots the recorded validation loss values over time, labels the points as test in a legend, displays the legend, and finally, shows the plot on the screen. This type of visualization is often used in machine learning to monitor model performance on unseen data and detect signs of underfitting or overfitting during training epochs. This code uses the pyplot module from Matplotlib library to create a line plot that shows the training and validation loss of a machine learning model over time, usually in epochs. The title of the plot is set as loss mean squared error. It assumes the presence of Historion object with loss and valclos data loss for training and validation sets. The validation loss is labeled as test and training loss is trained to differentiate between the 2 lines on the plot. A legend is included to clarify the lines, and the plot is displayed as a graph. The code snippet uses Python's pyplot module from Matplotlib to create and display a graph showing the mean squared error loss during the training and validation phases of a machine learning model. The graph is titled loss mean squared error and plots 2 lines representing the validation and training loss over epochs. The data for these lines is retrieved from a history object, and a legend is included to differentiate between the 2 lines. Lastly, the show function is used to display the graph for assessing the model's performance. This Python code creates a plot that shows the evolution of a machine learning model's loss during training. The title, axis labels, and legend are all clearly defined to aid in understanding the plot. This allows the user to easily track the changes in both training and validation loss over the course of training. The code creates a line plot to display the validation loss values of a trained model. It labels the x-axis as epochs and the y-axis as loss. The plot is shown using show, a common method to visualize a model's performance over time. It highlights the model's generalization ability on a validation set during training. The Python code provided can plot a graph of a machine learning model's training loss over multiple epochs. It uses the matplotlib library to do this. The plot command generates the plot's data by taking the loss values from the training process record. The clibble and dilabelch commands set the x and y-axis labels to epochs and loss respectively. The show command displays the plot, allowing the user to see how the model's loss changes with each epoch. This visual representation helps in understanding the model's learning progress. This Python code calculates the rms between the predicted and actual values in a training dataset using modules from the standard library and scikit-learn. First, the necessary modules are imported, then the mean squared error is computed using a specific function. The resulting value is then squared and the square root is taken to obtain the rms, a common measure for assessing the accuracy of a predictive model on numerical data. This Python code calculates the root mean squared error rms as a measure of the accuracy of predicted versus actual values for two sets of data. It is commonly used in regression analysis and has the same units as the target variable for ease of interpretation. The Python code calculates the rms between two sets of data, train and detrain predict, which is a measure of the differences between predicted values and actual values from the modeled environment. This is done using the mean squared error function from the scikit-learn metrics module, followed by applying the math such function to compute the square root. In short, the snippet evaluates the accuracy of a predictive model by determining the average magnitude of the prediction errors. This Python code finds the rms by calculating the square root of the maze between two data sets idist and predict. The mean squared error function computes the maze, which measures the distance between the predicted and actual values. The math such function then converts the maze to rms, commonly used to assess regression model performance. Lower rms values indicate better model performance. The Python code provided calculates the rms between the actual and predicted target values from a training dataset. This is a commonly used measure to assess the performance of a regression model. The lower the rms, the better the model fit. The calculation is done by importing the math and scikit-learn metrics modules and using the mean squared error function to determine the squared error in the math function to find the square root of this value. The given code calculates the root mean square error rms between the predicted values and actual values of a model for quantitative data. Rms is a commonly used measure of error that represents the average squared differences between the two sets of values. It gives an indication of the error's magnitude, with a perfect prediction resulting in a value of 0. This metric is frequently used to compare the effectiveness of various predictive models. The script uses a machine learning model named Model to run a prediction method, predict, on test data from test. It then creates an array or list of predictions, called predictions, based on this input data, to determine the number of predictions made. The len function is used to find the length of the predictions array. Please note that a line break or semicolon is missing between predictions model. Predict test and len predictions, as they are intended to be two separate statements. This code defines a function called floating in Python, which requires two parameters, a history and a titled. The function is likely used for data visualization, as indicated by its name. The history parameter likely holds past data or results from training a machine learning model or tracking a metric over time. The title parameter is used to label the created plot or chart. However, without the actual function body, the specific type of plot, libraries used, and the use of a history's data cannot be determined. Overall, the function is seemingly designed to create a visualization with a given title. The following Python code snippet defines a function called evaluate predictions that takes in three arguments: predictions, test, and outliers. The predictions is a list of predicted values, test is a list of actual values, and outliers is a decimal representing the percentage of largest differences to be considered as outliers. The function works by creating two lists, a ratio and a differences, which are used to calculate the relative error and absolute difference between each pair of corresponding values in predictions and chi-tests. It then determines the number of outliers to be considered based on the provided outliers proportion and the length of differences. Using a data analysis library called pandas, the function selects the largest values from a differences and returns them as a tuple along with ratio and differences. These largest values are considered as the outliers of the given dataset. This Python code snippet updates a data structure called outliers by using the values from another data structure called predictions. It does so by iterating over the indices of outliers and assigning the corresponding value from predictions to the same index in outliers. However, there is an unknown error in the formatting or syntax at the end where outliers is mentioned again without any clear context or purpose. This code uses Python and Matplotlib to create a line chart comparing predicted and actual data with outliers marked in green. The chart has a specific size and labels for both axes, as well as a legend to identify the datasets. The final code to display the chart is shown. This snippet uses Python to generate a plot comparing predicted versus actual values in a time series dataset related to standardized closing prices. It utilizes the Matplotlib's library and follows several steps. 1. Creating a figure and subplot with splt. Subplot, setting their sizes. 2. Plotting the predicted and actual values using labeled lines. 3. Identifying and highlighting outliers as green scatter points with thicker lines. 4. Labeling the axes and including a legend for clarity. The final output aids in comparing predictions and actual values, as well as identifying anomalies over different time steps. This code snippet uses Matplotlib to create a visual comparison between predicted and actual values over time. Highlighting anomalies, it uses various methods to set up the plot. Plot the lines and scatter anomalies and add labels and a legend. The result is a clear and informative representation of the data. This code snippet in Python uses the Matplotlib library to create a graph for visualizing data. The code first sets up a figure and axes for the plot. It then adjusts the size of the plot and plots two line graphs for predicted and actual data. The code also adds a scatter plot to show outliers as green dots and labels them as anomalies. The axes are labeled and a legend is displayed on the plot. Finally, the plot is rendered for viewing a comparison between predicted, actual and anomalous data points. This code in Python creates a graph to compare actual and predicted values over a series of time steps for a given dataset. The plot is sized to 10x6 inches and the number of time steps is based on the length of the predictions list. Two lines are plotted to represent the true and predicted values against their position in the sequence. A legend is included in the upper left corner to differentiate between the two lines. The plot also has axis labels for time steps and price at close standardized data. This type of visualization is often used in time series analysis and forecasting to evaluate the accuracy of a model's predictions. This snippet of Python code uses a plotting library, potentially Matplotlib, to visually display a time series prediction alongside its actual values. It creates a figure with specific dimensions, calculates the number of future data points to plot, and generates two-line plots representing the actual values and the predictions. The x-axis uses indices instead of timestamps, and a legend is added to the corner for clarity. The graph is labeled with the x-axis as time steps and the y-axis as price at close standardized data. The resulting figure is displayed to the user using the pult show function.